Hey, and thank you very much for coming. This is going to be a very, very different talk than what you saw previously. Okay, so last time I was here, which was a year ago, yes, I was talking about obtaining a European Research Council grant. And well, I don't know if some people were there or not, but basically what I'm going to present today is results, well, part of the results from this project. So these are by default high risk, high gain projects. So they're actually very rare in our conservative field of water research because you're developing something completely new from an idea. So this is why this presentation, Mira gave you a little bit of a global overview. This is very much related, but because one of the news that I read related to this wastewater directive is that at the EU level, in the next decade, they will have to invest 253 billion euros in upgrading the wastewater treatment. And there is going to be a significant role there played by decentralized systems, precisely also because of these smaller inhabitants number and so on, for installing the treatments. And well, because it also makes sense, it's so-called water for zero. Revolution, right? So this is what my group is working on. We work on, the title is Nanotechnology-enabled, but you will see that nanotechnology for us is an interface to enable electrochemical systems to treat water. So I'm going to start first from the very beginning, well, also because I'm reusing some of my old slides. So basically, like I said, water for zero, basically we will have to not only improve our wastewater management, but also employ new, for the first time, really new water and wastewater treatment strategies. And their electrochemical systems, they are really gaining traction in the last, you could say, maybe even 10 years. This is a technology that was mainly done in the lab, like with a little bit of something being mixed and, whatever. Nobody really cared about that. The big impulse for the interest in these technologies, I would say, was the fact that they are one of the very, very limited number of technologies that can degrade perfluorinated chemicals. And I don't know if now everybody in this room knows what is a perfluorinated chemical. I'm going to assume yes. So basically, I'll talk about it a little bit later. They have several inherent advantages, and so I listed them here. So they generally, unless you design them to do so, they do not require any usage of chemicals. So you bypass, several of these advanced oxidation processes are not actually feasible. Even if they could be efficient in the lab, they're not feasible to apply in the field because, for example, for Fenton reaction, I mean, this whole line of research is a little bit, I shouldn't say this, pointless. No, bad word. You need to, there are some limitations that you can never bypass in real life. Like if you need to go to pH 2 and if you need to separate iron sludge after that, that's not going to work, okay? So there's movements also in this field to improve that, to bypass, but there are technologies that are more or less feasible. Electrochemistry also has its limitations. So okay, among the advantages, what I have listed here also, they work at ambient temperature and pressure. They are generally very modular systems. So the upscaling is done by increasing the number of cells that you have, kind of like RO, reverse osmosis modules. And so the main advantage is this capability, in my opinion, one of the main advantages is this capability to defluorinate PFAS. So the disadvantages, and they are really, they were really long-standing bottlenecks to this technology. One is that they generally have, because we're talking about heterogeneous catalysis, they have low current and conversion efficiency. So that means that you need to invest a lot of energy to degrade your trace organic pollutants, as the names say. Well, they are present in whatever nanogram, microgram at maximum per liter level. So this results in high energy consumption. Another very important drawback that was often kind of omitted in scientific literature is that they also form toxic byproducts. In this case, the most important is these toxic chlorinated byproducts. Chloride is an ion that is naturally occurring. You will find it anywhere, in groundwater, in drinking water, anywhere. And this is a very electroactive ion. It gets oxidized very quickly to hypochloric acid, but also these anodes that we like to use to degrade organic pollutants to highest oxidation states of chlor, which is chlorate and perchlorate, and these are very, very difficult to then eliminate, okay? And this result here in the top, bottom right corner is one of the first results that I got as a postdoc in, well, this was in Australia when I started working in this field. The toxicity in my wonderful treatment was increasing like crazy up to whatever, even more than what I showed here. And this is actually not even due to chlorate and perchlorate. This, in this case, is because this chloride that you form reacts with the organic matter, just like in any disinfection process based on chlorine, and forms chlorinated byproducts. So not only things like THMs, HAAs, but also compounds equivalent to pentachlorophenol. So what we started with is that we kind of, the idea, let's say, the holy grail of electrochemical water treatment, in the end, the key here, the reactive design is crucial, but the key to enable the technology is the electromaterial. So we were aiming at developing one that has this high electrocatalytic activity for contaminant removal, but hopefully low electrocatalytic activity for chloride oxidation, so that we can control this toxicity, because there is no point in removing, I'm going to say ibuprofen or whatever, if you generated chlorate and perchlorate, okay? Then you just created another problem. Because of these high energy consumption aspects, that have to do with basically the fact that this is a heterogeneous, so surface reaction, surface catalysis, we were aiming at a three-dimensional electromaterial, and ideally we would have something that's like made out of platinum that would cost a lot of money and not be then feasible because of that, but something that is produced by a low-cost method. So the idea in this, this was I didn't even, I think, mention the name of the project. It was a ERC starting grant electrochemical water. We started here with graphene, but the cheap form of graphene. So in science, you will see that they call everything graphene, but it's not really correct. So we have the version of graphene oxide. This is normally nanosheet. So this is the dispersion. This is the image on the left-hand side. Which is an isolating compound. The perfect graphene, the one that you normally probably read about in newspapers, is this hyperconductive graphene on the right-hand side. The one in the middle is the one that we use. Okay, this is reduced graphene oxide. This is a semiconductor, and basically you restore partially these sp2 hybridized carbon, like the honeycomb structure, by reducing. We start from this graphene oxide. So this was really new at the time. It's actually still mostly used for the development of different cathodes, but to make a nanode, in general, to make an anode for electrochemical water treatment is a big challenge, because you need to go to very high potentials, very high currents, and it's very, very challenging there to obtain a stable material. So we were thinking how to make this three-dimensional graphene-based electrode, and so there's some working literature with these graphene, what they call hydrogels, aerogels, but as you see here from this picture, they are very fragile things that you can't really use for anything, maybe to publish your paper, but that's pretty much it, because you can't really connect them to current, you can't manipulate, they just crumble away in your hands. So you need a template to deposit this reduced graphene oxide, and the problem is what template to use, because since you have to go to high potentials, these typical templates that people use, like graphite, carbon felts, you cannot use them. So we ended up using, I had a postdoc, Luis Pires. He was really, really creative. He was not from our field at all. And I think that's very good. That's one of the best things I think about these ERC projects, that you can hire someone completely different. And this person brought new ideas. So here he managed to produce a material that uses mineral wool as a template. So this is mineral wool is something that you use in isolation of houses. It's this very cheap material that doesn't have really much of other purposes. But this is really silicate based, and what happens here in our process, we have formation of very stable, we assume this is covalent bonding between graphene and this silicate base. And this is the image that you see. Well, in some sense, this resulted in a material that has very easy synthesis. We can easily functionalize this graphene with different 2D materials, with atomic dopants and so on. The overall cost that we estimate is very, very low, because we don't use anything really expensive. It's also something that is, in this case, obviously structurally stable, which means we can manipulate it, we can press it against the current feeder, we can put it in our reactor, and so on. And this was also something that we protected with a patent that is now in national stages in Europe and in US. And the biggest surprise, I'm going to have to cut a lot of slides, but okay. So the biggest surprise about this material was the fact that for some reason that we couldn't really figure out. It would have to be something maybe done with modeling. Graphene, for the first time, reacted selectively when electrochemically polarized. What does that mean? So we saw this is, I don't know if there's any electrochemists here. This is this image here are linear sweep voltammetries. What this shows is basically you increase the potential. When you start having the reaction, your current shoots up. So these onset potentials, pointer doesn't work, no? Pointer? No. Okay, doesn't matter. So here around 1 volt, you have an increase in current because in this case it starts producing oxygen. Your material, this is the main reaction, water electrolysis. What happens here is that when we compare an inert buffer, in this case phosphate, that only makes oxygen, and sodium chloride electrolyte that should make oxygen and chlorine, we not even normally you would get chlorine production would result in this NaCl. The red graph shooting up much faster and leading to much higher currents than the blue one. And what happens here is even lower. So basically, this material is not oxidizing chloride ion at all. Why doesn't it do that? We don't know. This was I don't know, serendipity moment or whatever you want to call it. But so this was the first anode material for which we demonstrated there is no chlorine, chlorate, or perchlorate production, which was really important. This is when we also decided to patent, because one of these major bottlenecks of all commercial anodes, we do not have it. And then now this, I'm going to have to accelerate. If not, I'm going to take very long. So what we normally did throughout this project, we got, so we started with TRL, I guess everybody knows what TRL is, technology readiness level. So we started with one idea, and we ended after 5-6 years, let's say, together with COVID, at TRL4, okay, which means we demonstrated our technology in the lab and with realistic waste streams. We were always using these very small reactors here that you see in the image, like flow-through reactors, and we always did it in one-pass mode. And even when we use synthetic water, let's say, we try to use low conductivity, something as close as possible to real case scenario. And we would always do proof of concept studies depending either with, I don't know, hospital wastewater, with municipal wastewater effluent, with drinking water, with groundwater, with landfill leachate. So we treated all of these things. And this is just to illustrate how we do our studies. So we work with different groups of compounds. We work with PFAS, we work with antibiotics, we work with like bacteria. We study disinfection for drinking water. And we also work with just model organic pollutants. And these here that we chose, which is 2 X-ray agents with this triclosan is a personal care product, and diclofenac. These were chosen not because we cared whether they are on any list or anything like that. We chose them because these contaminants are very good surrogates to evaluate the performance of your oxidation process. What does that mean? They are very persistent to oxidation. You know, you can put there something that is very well regulated, I don't know, an antibiotic that is regulated and everything. But if this is something that you easily oxidize, I mean, it's not a big deal, to be honest. You can degrade it with almost anything. So we use these as model surrogates compounds due to their persistency to oxidation. So we would always do our experiments in one-pass mode, means there's no recirculation, just one pass through the reactor. And we would always investigate what happens only in the open circuit. This is this first OC, whether they absorb or not. In this case, for example, as you could expect, the green and the black, which is the 2 upper ones, they don't absorb at all. These are just normalized effluent concentrations, which we have on the y-axis, okay? And the bed volume equivalent to HRT, okay, more or less. And then we would apply increasing current densities to basically investigate the removal. So we have there different mechanisms in our system because we have graphene, we have, you know, adsorption, electrosorption, electrochemical degradation. So multiple mechanisms happening at once. This is also very interesting. So because we use graphene, our system has capacitance. This means that we can apply current intermittently and therefore lower the overall energy consumption. For example, here we applied current on and off, and we get the same removal or inactivation of Escherichia coli. In this case, it was, well, complete, you could say, up to 5-log removal of Escherichia coli from real drinking water in this one-pass mode without any chlorine. I have to emphasize there is no chlorine here. This is completely due to our nanostructured electrode material, so no production of these chlorinated byproducts. And we could lower the energy consumption from whatever, in this case, from 1.7 to 0.96 kilowatt-hour per cubic meter. So this capacitance is also very unique for our material because normally commercial materials that you buy that are based on metals, obviously there's no capacitance. You switch off the current and the thing stops. Okay, this is a little bit about doping. So basically by adding, for example, 2-dimensional materials like borofin, we can sorry, we can increase the generation of wedge radicals. Just here, if you look, for example, at this graph, the important one would be the gray bars. You can see that for just undoped graphene, in this case, just RGO, we have lower hydroxyl radical concentration than, for example, when we dope it with porphyrin, and these are really minimal amounts of dopant, just something so insignificant that we add and that has such a big impact. This is in terms of PFAS removal. It's a bit of a complicated graph. Again, this is how we do our experiments. So in this case, we did OC. We worked with 6 perfluorinated compounds, C4, C6, and C8 acid and sulfonates. And we could see always removal and degradation of all of them. But so here, the interesting thing again is this use of dopant, okay? So you can see here, first part of the graph is this open circuit. So they do not absorb actually at all. These compounds are surfactants. It's very difficult to make them absorb to anything. That's why granular activated carbon, for example, has limited capabilities in terms of PFAS removal. Then we apply current, we see that they are removed, let's say, and then always in the end, in all our experiments, we do this final open circuit, what we call OC final, to check whether anything that we removed was only electrosorbed but not degraded. So if we just kind of concentrated it. And we can see here, for example, the black ones are for the boron doped, so atomic boron doped graphene sponge anode. And here we have part of these PFAS only being electrosorbed, because you see how it shoots up a little bit in this F-line. And this is because we have only partial degradation. However, when we dope it with porphyrin that has this much higher efficiency in wedge radical generation, and this oxygen species figures in this unzipping mechanism of carbon fluoride bonds, there we actually, everything that we removed, indeed, we degraded, as you can see, it levels off. Okay, I will have to accelerate a little bit. This is too complicated. So I'm just going to show, sorry, I'm just going to, if not, I would have to give another 10 minutes of explanation. So I don't have time. We tested, so this is our, let's say, scalable reactor here, and we basically used the same material as in these small lab scale reactors, but then now we went to like units that are actually now used in the pilot that we actually just got yesterday. I don't have a photo, but it just arrived yesterday. So bigger pilot that would treat about cubic meter of water per day. And so there we can get complete removal or incomplete removal. The most persistent ones are the shorter chain. These are the empty symbols. The shorter chain acids and sulfonates, as you could expect, because for them we need to apply current for a longer time, because you really need to make them come to the electrode surface. They're just so polar. They normally fly through practically any treatment technology that we have available, not only this one. So we need to invest a little bit more energy. So what this is maybe the interesting part. So this started as an idea. It started as, let's say, kind of my brainchild, and it worked luckily. So from this ERC starting grant, we obtained, I obtained the ERC, it's called Proof of Concept Grant. These are smaller projects. They are only, so think that ERC starting is 1.5 million euros for 5 years. Proof of Concept is only 150,000 Ks for 150,000 euros for 12 to 18 months. In this case, it was 18. This smaller project enabled us to develop this prototype that, well, this is not our prototype. The last picture, 2025, it's, well, our prototype, but it's kind of like that. And so this will now enable us to go further up in our technology readiness level. And actually, the last success that we had is that we secured, so this smaller ERC proof of concept grant gives you access to apply for a European Innovation Council transition grant. And these projects are really great. So they are really, as the name says, they serve for transitioning from research to spin-off, because we are now in the process of establishment of this spin-off, that they actually have the same name, Graphic. And it is led by one of my former students. So not by me, but by another person in the group. In this case, this will enable us basically to advance to TRL6, because we will have on-site demonstration of our technology. We will also do additional research to improve our electrode material and obviously establish our spin-off. And we already have gained some traction with, let's say, with what would be the early technology adopters. So considering also Mira's talk before and the money and need that there is out there now in Europe, well, not only Europe, actually, it's also US, just they are a bit more advanced, but okay, now with Trump, maybe not. But so this need that in the first place comes from, I would say, from things like, well, they don't know what to do really with PFAS, and it's drawing a lot of social attention and pressure. We hope that, yeah, we'll be successful. So let's say, and I will stop here. I have more slides about the research that we did, but there's no time for that. So, do you have any questions?
Takođe, možemo da, imamo vremena i za pitanje.
Zato što sam kratila pola prezentacije.
Možete slobodno ko želi da pita i da bude neko tih da...
It's a bit maybe too technical. Šta da radim?
Mislim, koleginici, ali možete da pitate vezano za ove grantove, s obzirom da vidimo da ima puno iskustva sa njerskim grantovima.
Ne, sad smo na 4, znači, ali dobili, mislim, ja mogu da slikam prototip i kažem da sam ne više, ali to nije tačno, kako ti kažem. Prototip nam je stigao sad, bukvalno juče, i mislim sad mora to da otpakujemo, da testiramo, da organizujemo, mislim, to će trajati još nekoliko meseci, onda moramo, prvo će biti in-house demonstration. TRL5 kažu, mislim, to je kao technology demonstration in a relevant environment. Sad definiši relevant environment. U stvari, ključ će biti, ja mislim, ti on-site, ovo što treba da radimo u transition grant, ti on-site demonstrations, imamo 3 test sites, jedan je groundwater, jedan je landfill leachate i jedan je semiconductor industry wastewater. Zašto semiconductor industry wastewater? Zato što PFAS, neke industrije tipa food packaging industry is already phasing up. Ali neke kao što su semiconductor industry, to nikad, koliko naša tehnologija za sada zna, neće moći da isključe. Znači sve te produkcije tih čipova, a i u Europe ona ima taj EU for chip, jel, imamo tu ambiciju da ovde se proizvode čipovi i tako dalje. Dakle, oni će morati uvek to da koriste i oni, iako nisu zakonski regulisani sad u ovom trenutku, oni su svi u panici u smislu da bukvalno scramble for technology, znači da bi to regulisali. Tako da onda, i to je malo druga isto kompleksnija problematika, to nisu samo ni ovi tipični PFAS, PFOA, šta ja znam, linearni, nego oni imaju fluoropolymers. A fluoropolymers, to čak niko ne zna ni šta je to, zato što je to kao Coca-Cola, niko neće ti kaže koje je jedinjenje. Mislim, jer PFAS, ne znam sad da li ovde se publici je to poznato, njih ima preko 9000 tih CAS numbers. A od tih 9000 mi kao gledamo, ne znam, 24. Tako da, znači tu, samo od tih ostalih koliko ih ima, a još tek ti fluoropolimeri. Tako da je to užasna problematika, mislim, to je bukvalno tip of the iceberg, najblaže rečeno. Pa nisu regulisani, jer oni nisu, prvo što je, ne znam da ste gledali, ima jedan film koji to jako lepo objašnja kako je to počelo, Dark Water, sa onim Mark Ruffalo. To je odličan film koji prikazuje prvu civil lawsuit protiv DuPonta u Americi, zato što su istresali effluent i, mislim, umirali ljudi, umirale životinje i onda je, mislim, to je baš bilo onako direktno. Mislim, u Belgiji su bile više tih skandala je bilo. Belgijska vlada na kraju to kao settle sa 3M, jer su tamo u blizini Antwerpa isto tako imali koncentracije u groundwater nenormalne. U Italiji ceo Veneto region je isto tako zagađen. Znači, mislim, tamo gde tražiš, tamo ima. Ima jedan projekat koji se zove Forever Pollution. To možete googlovati, to je projekat Journalists koji su istraživali gde se sve nalazi PFAS po Evropi i markirali tačke kao hotspots. I to je nešto što bi trebalo vlade da urade. A vlade to ne rade. Mislim, i oni nemaju stvari tehnološki odgovor na to. Ono što industrija trenutno koristi je apsurd, zato što je to granular activated carbon. Znači, oni koriste granular activated carbon da odvoje PFAS iz nekog landfill leachate i onda taj isti GAC ide na taj isti landfill.
Da.
Znači, oni nemaju stvari, ne mogu toliko ni da regulišu konkretno dok ne mogu da predlože neko rešenje. Tako da... Nije baš najbolja situacija. Pa podrška su projekti koje mi dobijamo.
Da.
Podrška su projekti koje smo mi osigurali, da. Pa dobro, to se ide preko advokata, mislim, za to i sad mi smo do sada dosta bili uspešni u tim nekim kompetitivnim kolovima za treninge, imaju ti neki sad deep tech accelerators, deep tech, dakle to bi bila bilo koja tehnologija da nije IT, ne znam, artificial intelligence, nego da baš imaš neki proizvod i koji je nova tehnologija, a ne dodao sam app. I sad ti deep tech accelerators ima ih puno, mi smo u jednom učestvovali, dobro u više njih, jedan je bio baš dobar recimo i sad tu stvari, tu ti je koji svugde ključ networking, mislim i da se povežeš sa ljudima koji imaju nameru da investiraju nešto tako rizično, jer je to rizik, mislim. Ne, vlasnik patenta u Evropi je uvek institucija, uvek, znači stvari, ti si samo inventor i onda sad ti pregovaraš sa institucijom da se licencira ekskluzivno na taj spin-off. Imaju sad tu više načina eksploatacije, možda možeš da ga licenciraš ako hoćeš neku kompaniju, ali to nije naša ideja, dakle mi hoćemo da ostablišemo, da osnujemo. A vidi ja što pričam, ovdje nema mikrofona.
Ja htjela da vratim u nekom trenutku, ali se...
Možeš da, znači naša ideja je da osnujemo kompaniju, spin-off i sad da guramo koliko možemo sa tim. Pa ako jedan dan moramo da prodamo nekome, pa prodaćemo, ali za sad je to više onako kao, kako ti kažem, lični projekat naš.
A i naši ljudi.
A dobro, CEO spin-offa, njega ste upoznali, on je odličan networking. Tako da sad tražimo u stvari nekog ko bi nam bio komplementarniji malo u biznis smislu. Što se tiče research, tu nema problema. Znači, nam u stvari treba neko ko će da se bavi... Pa da. Tako da. Sreće.
Dobro, da li imamo još pitanja?
Ako nekoga zanima kako se dobije, jer svi možda priča.
Tako je.